Hi class, this is your instructor Dr. Mayas, and today's subject is from chapter 15. The third subject is the impact. So you learn the mechanics of impact, which studies the motion of bodies undergoing a collision in two different types, the central and oblique. The new terms that you will learn is the coefficient of restitution, which will be used together with the conservation of the momentum and the principle of momentum and impulse to solve impact between bodies. In problems where you don't have enough information about what happened between two bodies, um, let's say a tennis ball is hit against a wall and you want to know how the tennis ball will move afterward as a result of that impact with the ground. The information typically provided to you in the previous sections gave you the ball trajectory, the velocity and the angle. And probably ask you to calculate one of the unknowns, given that at most we can get one equation or two equations if it's asking you to calculate the components of the velocity in x and y. Now, sometimes we know more about the quality of the ball and the ground, and this quality can be measured in case of impact, can be measured by using this coefficient of restitution, which will tell you, for example, how elastic or plastic the ball is. And the best way to look into this problem is we know that tennis ball that's bounced more is better, right? So if a tennis ball is let go from a certain height, say 1 meter, and bounces back at 1 meter, this means that tennis ball is perfectly bouncing, which definitely doesn't always exist. So we expect that the ball to bounce at a height less than the previous one, simply because of the losses. So that measurement can be obtained using this coefficient of restitution, which will show you how to calculate. Another application is the billiard game. Knowing initial velocities of balls, and we want to know what happened after. Given that we know some information about the materials used for making these balls, which will translate into the coefficient of restitution, we will be able to know the trajectories of these balls after the impact. So, in summary, an impact occurs when two bodies collide during a very short time. This will define the principle of momentum and impulse, which will cause a short but large impulse forces that exerted on the bodies in opposite direction and causing them to deter and move different directions, or maybe together, depends on the problem. So what's important to define here is a few terminologies. We want to define the line of impact, which is a line that passes through the centers of these masses. So let's say we have a mass A and a mass B. Their centers, or the line that passes through their centers, is called the line of impact. And the line is perpendicular to that line of impact is called the plane of contact. This is important because the line of impact is where all the coefficient of restitution equation and also the conservation of momentum could happen. On the other hand, about the plane of contact, which is perpendicular to the line of impact, the conservation of momentum can be applied for each individual mass, as we will see there. Now, knowing that these equations are vector, we'll end up with four equations. Two equations from the conservation of momentum about the line of impact in x and y. In y for each mass. And the coefficient of restitution which provide us another equation and the conservation of momentum about the plane of contact. All that together will be used to solve impact between two bodies. In addition, we said that the types of impacts can be classified into a central, which occurs when the direction of the motion are in the line or parallel to the line of impact, as in this figure, and the oblique impact when the direction of motion of at least one or both particles mass A and B have an angle with the line of impact. So it's important to emphasize that to establish the central to know the line of impact, you need to know the classification. And the first step is to draw a line between the two masses that will define the line of impact. Also, it's important to notice that the impact, this is about the line of impact, the deformation takes place as a result of this momentum. So let's say two bodies, A and B, colliding, and we know that if we take the free body diagram, or the momentum diagram of one body at least, let's say left, the impulse force will show, right? Or if you take the B1 and then you apply the principle of impulse and momentum, it will appear. Together, you will be able to derive the coefficient of restitution. As we mentioned earlier, is when you use the central impact, you don't need to have X and Y component because the direction of the masses are along the line of impact, so it's sufficient to use the conservation of linear momentum for the two masses before is equal to the two masses linear momentum after. Now, as we mentioned generally last lectures, at least one of them were known to be able to solve for the unknown. Now, in this lecture, the coefficient of restitution is another criteria that defines the quality of impact between two bodies, and will be used together with this to give us an insight how the velocities will move without knowing any information about any object's velocity after the impact. So this will help us determine that. So what is the coefficient of restitution? Let's say we have a central impact, again where velocities defines the or is along the line of impact. Then the definition becomes easy to obtain, which is E equal to the relative separation velocity divided over the relative approach velocity of these two bodies. And this is always less or equal than 1. Now, E specify this relationship where this equation is obtained from analyzing the momentum diagram of each body and then combining it with each other, and we'll end up with that definition. So if we know that, and we know the relative velocities after, divided over the relative velocities of approaching velocities, which is before, and you notice here, when you subtract the velocities, which are vector, VB minus VA after, divided over the VA minus VB. So make sure that you switch the order. And this is all depends on the direction. So if we have to establish the coordinate system. So what's the meaning of the coefficient of restitution? A perfect impact when there is no losses is when the relative separation is equal to the relative approach, meaning that the total energy is conserved. So that can be used. Also, the total the largest or maximum energy loss will be such that when the two bodies collide and form one body, and this is called the most plastic impact, where the relative separation velocity is zero because the two bodies become one, or they stick together. Typically, in between, the values will depend on the material and the finishes. Let's say steel on steel impact have that range, 0.5 to 0.8, while glass on glass has higher impact, which means less losses, and that losses, I think, it's due to the sound. While if you have wood to wood impact, it has really roughly medium range, and lead to lead mean or lead to lead means it's lowest or highest losses. So talking about losses, if you want to compute the energy losses during the collision, it's simply estimating how much energy difference between or after the impact as compared to the total energy before the impact, which means we're talking only about the kinetic energy losses, assuming all these impact happen on plane, not a vertical, but as planar coordinate system where the potential energy is not into consideration, so that we can compute the energy loss here by the difference in the kinetic energies. And definitely this amount shouldn't be at the best is zero when there is no losses, which is nearly impossible. And the maximum energy loss happen, as we said, in the plastic collision when the two bodies stick together, but not necessarily equal to zero. Going back to the oblique impact, as we mentioned, this oblique impact happens when the velocity vector of one of the bodies has an angle with the line of impact, such as that. So this is two centers and pass a line. This is an oblique impact because we have an angle. So we expect that as a result of this impact, each body will take a different trajectory, which is defined by a magnitude and an angle. So to solve for four unknowns, right, we have 1, 2, 3, 4. Typically, most of the problems give you what happened before the impact, and then ask you what's happened after the impact, which means calculate the magnitude velocity of the body A after velocity vector, which comprises of the magnitude and an angle, same as for the B. So this is for unknowns. So here's the how you obtain the four unknowns. First of all, you establish the line of impact by connecting the center. Now that's going to be giving you the line of impact. The impact plane is perpendicular, so it's in Y. Second is you establish your coordinate system, so you make your coordinate system along the line of impact. The first thing you will do is apply the conservation of momentum about the line of impact. That will give you the component of these vectors applied before and after, right? And that's one equation. So in this case, this is what we have. The second equation you will apply is from the coefficient of substitution, where you know the relative velocity separation of due to the line of impact velocities. So this is important to notice. This is computed along the line of impact, so we are only concerned with the x component. So this is the relative separation over the relative approaching, and that's going to give you the second equation. Now, another equation that you will be needing to apply or to calculate these four unknowns is that the momentum of each particle is conserved in the direction perpendicular to the line of impact. So if that's true, then nothing will happen to the velocity component in the y direction. Because when we say that the momentum of each particle is conserved, knowing that the mass is constant, then what happened after the linear momentum before equal to linear momentum after, and because the masses are unchanged, most circumstances, right? Then they say that velocity component in y is unchanged. But keeping that for generality, we're gonna write it in this form. So that's same for the part B. So that's gonna give us the 1 and 2, 4 equations. So this is the two more equations, the 1, 2, 3, and 4 with 4 unknowns. Okay, so let's summarize the steps and take an example after that. So first, gather the information about the problem, determine whether it's oblique or central, and establish the line of impact. Make your line of impact along the x-axis and make your y-axis perpendicular to the line of impact, which will define the impact plane. Apply the conservation of momentum along the line of impact using the vectors component, and also apply the coefficient of restitution along the line of impact for both central or oblique. This is true. More particularly, if you have oblique impact and you have 4 unknown, you need 2 more. In that sense, you need to add 2 more equations, which will come from the conservation of linear momentum for each particle, where you apply that the mass by the velocity in the y direction is equal before and after for each part or each mass. And that's give you 2 equations. So let's take an example. Alright, so when you have here a ball striking a smooth wall with a velocity, initial velocity 20 meters per second, whose angle with the a line, let's say x, and later we'll define what does this line mean, is 30 degrees. It's also given to us that the ball and the wall has a coefficient of restitution is equal to 0.75. Notice this coefficient is unique for the ball and the wall, and it could change depending on what wall you are striking and the surface roughness. So there's a lot of factors. Now we want to calculate the velocity of the ball just after the impact, right? Previously, we would, to give you, if we didn't give you that coefficient of restitution, we would have given you at least one piece of information, and then we had one of the examples solved previously. In this problem, however, we're not telling you the angle or the magnitude, we're just giving you an information about the properties, which is coefficient of restitution. Alright, so what are the steps? First of all, we need to establish the line of impact and choose our coordinate system. So now we have 2 masses, right? We have a wall and a ball. This wall, I know it's big and infinite, so we can consider its center of mass to be centered along the line that passes through the center of the mass for the ball. So therefore, if I would consider this point to be the center of the mass of the ball, and this big wall has a center of mass that is centered to its geometry, then I can draw this line, right, this line, to define my line of impact. And this is line of impact. I'll choose a coordinate system that is x-axis, whether it's left or right, positive direction, it's up to you, to be used in that direction. So the 30 degree, so this is the line of impact. The plane of impact is perpendicular, which is in y. Alright, so given that, so the first step is to apply the momentum of the ball, or the conservation of the momentum of the ball in the y direction for each So we know that the wall is not moving, so velocity in y equal before and after for the wall is 0, 0. So not not more not that gonna add any information. But for the ball, we know that the component in y of y before the impact VB multiplied by its mass, which will give us the linear momentum, multiplied by the angle, which will give us the component of the velocity in y, sine 30, is equal to the after. So what we'll get is m mass of the ball multiplied by the 20 multiplied by sine 30, which will become together the VB1 before the impact, equal after m VB2 multiplied by the sine angle, which is unknown. Masses will cancel out and you'll end up with VB2, VB after sine theta multiplied by 10. So we have two unknowns and we need two more equations. Now remember that the line of impact you can apply coefficient of restitution. So coefficient of restitution is only considered for the component vector velocity vectors along that. So it's only for the VBX before and after. So before and knowing that the velocity of the wall is 0. So let's consider the speed of separation, relative speed of separation divided over the relative speed of approaching. And we have to remember that switching the order. If we choose that this is the wall that has a 0 before or after, right? And that the velocity in x direction is going to be VB2, right, x, and I'm going to put a negative because my x-axis and the vector here is opposite, multiplied by the cosine angle. That's going to define the component of the ball velocities after, divided over the relative approach. And so this is a positive 20 because the component 20 cosine 30 positive in the x-axis minus the velocity of the ball, which is unchanged, is 0. So that's going to give us another equation where you write VB2 cosine theta equal to 12.99 meter per second. Great. So we have one equation here, and we have here one equation. So we have two equations with two unknowns. Do we need any further equations? No need. Honestly, you don't need any, although you could in some circumstances when you have more unknowns, you need more equations, which you could obtain by conservation of momentum along the x-axis, which will be, in this case, you don't need to apply it, simply because the coefficient of restitution is given to you. And then, therefore, you solve for these two unknowns by squaring equation 1 and equation 2. You square both of them and they add them, right? And then the sine theta square plus cosine theta square, and the component VB2 is outside, so that's what you get. So this is how you solve it. I can switch to show how is that solved. So equation 1 says that the VB2 cosine theta equal to 12.99, and equation 2 says that VB2 sine theta equal to 10. So we have 1 and 2, square both of them, so this is squared, everything squared, so this is through operation, and then add, right? So you're gonna get VB2 square cosine square theta, right, plus VB2 square sine theta square is equal to 12.99 square plus 10 square. VB2 square cosine square theta plus sin square theta equal to 2.99 square plus 10 square. This is trigs. From trigs, this is equal to 1, so you're going to end up with vp2 square equal to this amount, and then you square root it. 99 square plus 10 square, and that's going to give you 16.4 meter per second. And you can find the theta from any of the equations here by substituting the magnitude. So that's going to solve for theta and VB2 magnitude. Alright, let's take a look at this concept quiz. Two balls impact with a coefficient of restitution of 0.79. Can one of the balls leave the impact with a kinetic greater than before the impact? Well, the answer is definitely yes, because nothing has said about the masses. While the total energy cannot be exceeding before the impact, but this is can one. So the can one of the balls leave? No, we don't know. So that's not a factor. So the answer is yes. Under what condition is the energy lost during the collision is maximum? So if you think of the equation or the kinetic energy difference, when the kinetic energy difference is the most, then you get that most energy loss. And the most is when the two bodies stick together and have the same velocities. So the answer is B. Alright, now a group problem solving that I will leave for you to try at home. Let's here to discuss the problem statement. We have a tennis ball served horizontally at a height of 7.5, and it strikes the ground at B and at distance 20. Knowing that the elastic or the coefficient of substitution is between the ball and the ground is 0.8, calculate the initial velocity A and the rebounding velocity B. The first part is to calculate VA. Now this is regardless of what happened after the impact. The first part of the problem is simply follow the projectile motion analysis, where you can compute the flight time that it takes this ball to go from A to B using one of the equations, and then use that flight time to along with the knowledge of the distance traveled to calculate the horizontal component of VA, which at this moment for the initial velocity was VA along VAX. So these two will give you how much is the velocity VA. Now to calculate the velocity VB, you need to know the velocity VB before its impact. So that's how it must be calculated. And again, following the same analysis of the projectile motion, you will be able to calculate VB before, right? So so what happened before and after, it becomes a simple problem that we discussed many times, a ball striking a ball. So look into the solution and try it. Make sure that you define the properly the line of impact, and also calculate the flight time, which here to be 0.68, and then knowing the distance, you can calculate the VA simply because the no acceleration in horizontal direction, so that's going to give you the distance. And then you can apply the coefficient restitution. So this VA, so VB note, you can calculate VB note from another equation, and using the VBY, and VA is constant always, so you'll be able to know the VAX So this is VAX. So VB naught has two components. VA, which is equal to VBOX, and also VBOY, which can be obtained from the equation of motion for a ball falling into a trajectory, and knowing the flight time, so you get that. So you have two components which define that motion. So having that said, you can apply then the coefficient of substitution to define what's happened before and after, right? And since the rebound happened on the y direction, so the line of impact is on the y, so you only consider for the VBY node, right? And you can calculate the VBY. Now, in this problem, you will notice that because, first of all, there's no acceleration in the x-axis, VA equal to VBOX. And also because the line of impact is in y direction and the plane of impact is in the x, you expect that the momentum of each particle, like the ball in the x direction, to be conserved, meaning the VAX is going to be equal to VBOX equal to VBX. So it will not change. So it will keep bouncing at same level of velocities and then start to roll. So if you want to plot how this problem will look like, so it's gonna look like that, and bounce and bounce and bounce and keep having a velocity, so keep rolling, right? This height decreases because E is 0.8. It's less than 1, we have experienced loss of energies. And you can figure out the height ratios, right? So this keep bouncing. As an exercise at home, do the analysis here for a second bound. Let's say at B and C, what happened at C, and find the relationship between the first bounce and the second bounce and third bounce. And so keep applying the conservation of momentum for every bounce and see the relation between the height, maximum height, and also between every bounce. And with that, we finish this section. I'm gonna record also another section for the next meeting. Please, see the assignments that is posted, and I'll see you next time.